Hey everyone, so today I will be presenting a paper in which the authors basically tested a lot of different ways to estimate functional connectivity from the MRI data, compared the results between each other and a few uh, benchmarks they defined for themselves, kind of, I suppose. But anyway, I think we can start. So let's start with some general information in case you didn't work with functional connectivity and what is it in the first place. So, generally speaking, brain connectivity describes how different brain regions interact with each other. You can imagine brain as a graph where nodes of different regions, they send signals to each other and do something like that. Functional connectivity tries to describe those connections with statistical tests. Basically, if you have some recording of brain activity, you can apply different statistics and try to derive the interactions between the signals from different regions. Usually it is, from what I saw, people are usually using Pearson correlation coefficients, which are based on the covariance estimation between two different signals. And that was real information. But Pearson correlation and covariance isn't the only way you can compare your signals. There are many families of different tests that they can estimate different things, they can work in different domains and use different data. And there is a lot of them. So what this paper did is basically it took a lot of different tests, tried to categorize them into different families, and compare them on the FNC derivation on the HCP dataset. So let's start with the families of statistics that they try to use. So there are different ways to estimate the correlation, the interaction between different time series, different data. Covariance family is one of them. It is basically, well, it's based on the estimation of covariance and deriving different metrics from that. Pearson correlation coefficients is one of the examples. There is precision methods, which, as I understand, are basically the inverse of covariance. Another family is the distance-based statistics. They try to estimate the distance between the signals or some representations of signals. Like in the trivial case, you can just compare the Euclidean distance between the two signals. In a more complicated case, you can try to synchronize them, and time work with this kind of work is doing that. Then there is a causal family. It's a group of methods that try to estimate the directed effects. Say, for example, if some brain region is affecting another brain region, those methods should be able to pick it up from the data. There are many examples, and I think they can work quite differently. They try to unify them under the causal umbrella, but they can be quite different. They didn't try gradation causality for that. I don't know why. They tried additive noise, and
it was there on your previous slide.
It was, but they attributed it to the spectral framework. They use spectral gradation causality. Yeah. I'm not sure if it's the same. There are 6 families. The fourth one is based on the information theory. It's basically all the stuff about information entropy and joint entropy and mutual information between different sets of data and so on. And the last one is spectral friendly. It's based on the decomposition of signals over the frequencies and comparison of their energy in different frequency bands, or just comparison of their phase, lock-in, or that kind of thing. It is especially useful in EEG when you're working with EEG because it gives you data with high sample rate, so you can analyze it in the frequency domain quite well. And plus, you can really use the covariance-based methods with EEG because EEG signals are very correlated because of the brain in the skull, and skull is conducting the signal to the nerve master. So these were the families of different statistics, and this is the primary scope of this paper, I think. It is quite dense and big. I'm not sure if it's really informative, but what it shows is basically the average similarity between the FLCs derived with different statistics. So each row and each column here is a different method, and each pixel is a measure of whether the FLCs derived with different methods are similar or not. Blue is dissimilar, red is similar, and white is very quite different. Can really compare similarity.
But it's still correlation. So they're not different, they're just anti-correlated if they're negative.
Well, yeah, it's like anti-correlated and correlated, kind of more similar than not correlated.
Yeah. So 0 is they have nothing, no relation.
Yeah, blue is just the same with the opposite.
So this matrix on the screen has those columns and rows listed there.
Yeah. So you see they categorize those families of tests, and each family has different subtests, like covariance or precision, so on. And each of them is having 7 more subtests, something like I guess Pearson correlation or some comparison covariance. I'm not sure if this is a beautiful result, but I'm not sure if it's really informative, because it basically allows you to compare how similar different methods, but it doesn't tell you much more. It doesn't tell you if those methods are working like the same way or something like that. And
do they mention anything about it in the text?
I don't think so. Well, they basically describe that they compared a lot of tests on video.
So what data was used to generate this matrix? Is it like an entire data set, many data sets, an average, or
So they started with a ACT data set, about 300 subjects. For each subject, they derived 300 FNC. So for 300 subjects, they derived 300 FNCs. Then they compared each FNC, each subject. Sorry, they compared FNCs from the same subject, but different method, and then they arranged the result in the slides.
Oh.
And then they showed this. Yeah, it allows you to compare how similar different FNCs are, but not much more. The next result, I think, is more interesting. They wanted to test if different FNCs, if different methods can be used better or worse for the subject identification and the behavioral prediction. So to identify subjects, they took subjects from the HCP dataset with several recordings. They derived FNC for each one, and they compared the mean of the subject FNC and the mean of the whole dataset FNCs. And they derived this metric, which compares the difference between the means divided by the variance. It kind of allows you to tell on a very high level if the data is separable in theory. And so they found that the methods are generally, most of the methods can be used for fingerprinting with more or less the same result, some others. But there is a precision family which is surprisingly good. And it is based on the inverse covariance.
So precision family, precision matrix is, yes, inverse covariance. If your data is truly Gaussian, those are the relationship. It's partial correlations basically remove everything what remains, remove everything but those two what remains. So equivalent to compute covariance and inverted. And again, there are things that are called Gaussian graphical models. So if your data is Gaussian, then this is the identified relationship to second order. And Gaussian only has relationship up to second order. But people don't like precision, even though it's much more reasonable in terms of interpretability of what's going on for relationship. But in the brain, and even in genetic expression arrays analysis, they don't like precision because they don't see the results are sparse, and they don't sell to be to be blunt about it. It's like people like to talk about small world networks, and in correlation matrix they see small world networks in precision. They don't see those sexy effects. So even though if you take masses on a spring and you start wiggling one, the correlation will be completely complete matrix, everything related to everything. Precision matrix will be exactly correct. It will be off diagonal. But yeah, nobody cares, I guess. It's like, I mean, there are other considerations, not to be that rough, that people like don't like precision. But yeah, that's good. Partial correlations, right? I mean, there's no magic there either.
But this is basically, this was done just for the one HCP, or which data set was this done for?
They only trained HCP 300 subjects.
Oh, okay. Well, I guess you would need to do this for any new data set you wanted to use and maybe potentially take the highest, most identifiable metric, depending on what you're trying to do.
Yeah, I mean, but how, again, the question is how significant is this identifiability? Yeah, like maybe, I don't know. The interesting part about, yeah, so this is what are they building? A predictor, like a classifier?
In this case, they are just comparing the data without trying to compare the means. So it's like a very high level overview of data set. The score is high, it's highly acceptable. If not,
yeah, like when we're looking at correlation matrices or at FNC's functional network correlations after ICA, we're also looking at a predictor using them as features, and if they're good features or not, and they're usually good features. Like JDX is better feature than just simple. It's not just Infomax, etc., etc. There's a proxy probes into whether this is informative thing. What we're doing is like that as well, kind of a proxy.
Mm-hmm. But I guess, so like the identifiability thing, is it kind of like a measure of how different things are between subjects, or, okay.
they call it fingerprint because it's how well can distinguish the subjects.
So these methods are better for capturing like differences between subjects, whereas maybe there's some better measure for like group level differences.
Yeah, that kind of, I guess that's kind of thing that can compare, check on paper, different aspects of what you can try to do this. Yeah, another thing they basically assessed how different FNCs can be used for prediction of brain behavior. And they did it in some interesting ways. It may be overcomplicated, but they took the demographic data from ECD dataset, that's something like 100 entries, and they applied ICA to it and found 5 most prominent components, and somehow assessed how those components, how those behavior things can be predicted from the different FNCs. And what they found here, again, is that some methods can be potentially better for finding out, for predicting some kind of behavior, but is I don't know, I don't see any clusters here. So maybe the covariance family is behaving more or less the same. They seem to be more or less the same for the prediction.
The fact that there are stripes means
Well,
that
yeah.
they're kind of the same.
I don't know.
I mean, they're not perfect stripes, but
Outliers are just
yeah, CDS is not good at all. Side wavelet is
looks
weird,
flat. Looks flat.
but it's supposed to be flat. So it's not predicting anything that's near zero.
Mm.
And side is like that. Okay.
Oh, that's one.
Yeah, it doesn't trust my accent. Sorry. I was filling out something for my school, and I need for this child. Sorry for off topic. And he's like, write something short, otherwise you make spelling mistake, and they will take points.
Okay, next they compared more technical thing, just the spread of the connectivity strengths in different methods. And they found that some methods are producing more uniform connections with the same strengths, some are more diffused. But again, I don't think it is especially effective. Just
But that means we're flat, right? It's kind of flat, right? Well, precision, the problem with precision is there are not too many connections. This is not compatible. Precision will be like only 5% of them are non-zero. And yeah, they are similar, they're only high ones. And also with precision, you can actually run statistical tests right there, right? And keep only those that pass those tests. So I don't know.
Next, they compared the hardness in different frequencies. Hardness is basically a measure of how much your regions are connected to other regions. It just calculates the average strength of connections from each node. And they compared it again. So you can see that there are bands stripes that look like they are opposite of the other regions, but it stems from basically the fact that those methods are measuring different things. Covariance-based methods are measuring the correlation, the similarity between signals. And for example, precision is measuring something more like a distance. So the values they give are kind of the opposite.
No, precision measures more causal correlation. Precision measures correlation with all other confounders removed. Correlation
Yes,
is
I guess it's
not this.
about the connections it is highlighted. Yes. It's just in Pearson correlation, if you have a strong correlation with something, you have a coefficient 1. And I guess
Same with precision.
0.
No. Precision is strong correlation of 1, but what correlation means is remove the confounders and then correlate.
Mm-hmm. Here is a comparison, but it's not precision.
Yeah. Precision is the same correlation. It's the same. It's called partial correlation because it removes the confounders and whatever is left. Then, so you have A and B and other variables. You take everything in other variables and regress them out of A and B. So you remove from A and B what is present. I mean, roughly what is present in other variables, and whatever remains, that means it's not due to other variables, kind of. there's a circularity argument there. But yeah. And then you say, okay, those remainders, the residuals, are they correlated or not? It's still correlated. It's still correlation. It's just math works out in a way that the dual of covariance is precision. But in effect, or semantically, what you're doing is you're removing the other effects. Totally, like it's an interesting subtopic about dual spaces, like frequency values versus matrices and their inverses. Yeah, like in frequency and values, the same. If frequency space is dense, that means likely that the value space or whatever it's called is sparse, or there are sharp corners, and reverse. With covariance, the same. With inverse, sorry, of matrices. If your matrix is sparse, the inverse of the matrix will likely be dense. If your matrix is dense, the inverse will be dense. Yeah, probably there is a relationship with the Fourier spaces, although I don't know.
There is one thing they mentioned about the hardness. I guess people are using, when people are trying to find the networks in the brain, they're using those hubs as a way to tell if something is network or not. And here we can see the different methods can produce very different pictures with or without hubs. And who knows, maybe if this figure, if the rows goes here reshuffled in a way, maybe we will see different hubs and different networks. But okay, that was another thing we tested. Next is the weight distance relationship. So there is a thing that distant brain regions are supposed to be less interconnected with each other. And so in the data, you should see that the correlation of the connectivity strength should be anti-correlated with the distance between regions. And the higher the anti-correlation is, the better the method is aligned with this relationship. And what they found again is that mostly all of the methods are somewhat anti-correlated, except for methods that are supposed to be correlated with precision. And some of them are better, but not that much. So I guess we can say that they all are more or less the same with respect to this relationship. And I'm not sure if what you said before like aligns with this.
I don't know how they measure it.
Well, it's like you have an FNC, and each round goal in FNC corresponds to a region. Those regions are spatially arranged on some distances, and they compare the strength against the distance. How they correlate. If the distance is small and correlation is high, that's kind of the behavior what they expect from the FNCs.
Negative correlation doesn't mean it means still high correlation, right?
Yeah, but that's what they expect to see. Negative correlation of strength with the distance. The closer the regions, the more interconnected they are, and the stronger is connection.
This is just so there is math and there is explanation. What you're saying is a story. For partial correlation, the math is just simple. The story that partial correlation is yeah, blah blah blah. You need to regress out everything, but using linear regression. Yeah, it is as I said. You regress out, and practically correlate the residuals. So it has nothing, the definition and math has nothing to do with distance or anything. It just shows you what it matters. It shows you correlation of each of the node in a graph for each time series when other time series have been regressed out of this time series.
Okay.
So
This whole result is just a benchmark for FNCs. It's just people expect that close regions should be more connected and distant regions should be less connected. And it should result in an anti-correlation between the signal strength and distance. And they show it on the screen. Most of the methods, except for all of those that are correlating positively. But they explain that methods that correlate positively is that are measuring the distance. It's like their connection strength is based on the distance.
okay,
And so we have this picture that they are positively correlated. Sorry, maybe distance is wrong. What to say? There are methods that measure similarity between the regions and dissimilarity. And these similar methods give you positive picture, and similar methods give you negative harmonic correlation.
Yeah, partial correlation measures similarity of the residuals of given the confounders, remove the confounders. It does not measure dissimilarity. It's just correlation. The higher is the measure, the higher is correlation of residuals. So you remove the confounders and what is left. Yeah. If you want, you can pull up the partial correlation Wikipedia on the screen. I just don't have it. And it's just a correlation definition of the distance.
I guess in case of precision, maybe when you regress this shared thing, you're basically removing the similarities, and what you're left is dissimilarity.
No, I'm removing other effect. What is left, if it's correlated, then they're similar by themselves, not due to the effect from others. That's the thing. I'm just thinking about rather like trying to get it back to the example with masses and springs connecting them. There could be like how they measure distance. How they measure distance. Do they measure just Euclidean distance? Like they take center of mass and measure the distance, and that's interesting.
Yeah, I was confused about that as well. It says they use interregional Euclidean distance, so physical distance between brain regions.
Yeah, so they presented brain regions as dots, center of masses, or something like that.
But it seems weird to me with something like the default mode network, which is like span across like multiple proteins.
Yeah. But they took some atlas that is localized, etc., and then that also they broke correlated things into different regions. And then, so yeah, like that's actually a perfect point that people have like. So if we have a thing that we see like those things act together. Why they act together, I don't know. Maybe there is a shortcut connection here that we don't measure through the corpus callosum or something like that, but they act together. If they didn't use ICA components, okay, let's try it, right? And said, oh, this is one region, this is another region. Those things correlated perfectly as one. They're far, but they're different regions. They will show up there. So that's
yeah, but I guess this can be true, but in general it isn't. In general, distant regions tend to be less connected.
no homologs. Almost all of those regions are acting together left and right hemisphere, and they're the farthest apart. but they're connected by a shortcut, right? Usually through
Are they
cortex.
connected only to each other? Do they have this shortcut only to each other or to other regions too? Because I understand.
No, they connected to everything. Say
Mm,
this is a thing that makes them related, but and they're connected to everything. So imagine a simplified situation that this thing is a driver. It's a parrot. It doesn't receive any signal from others. It only broadcasts signals. Then your correlation says, ooh, spatially everything is correlated. But then this signal around is the same as here. Ignore it. This signal around is the same as here. Ignore it, ignore it, ignore it. So you remove all that, and all that's remained is those two are connected. They're the most distant because this signal around them is the same. It's already there. It's like we removed it because it's a confounding factor. Because again, my example, simplified example, is this masses on a spring. This is highly correlated with that. This is highly correlated with that, right? But you will only.
Okay, but we don't actually remove it.
Hmm?
But when we can compare some correlation, we don't remove this.
Yeah, exactly. That's what your blue line shows.
Yeah.
All nearby things are correlated. But all nearby things are not unique. It's the signal that transmitted by that partial correlation says remove confounding factors. So if we do this and put a connection here, but spatially they're different, and your correlation will make all four of them correlated. Because like you know the problem with ordering in this matrix, right? The ordering will change how the matrix looks, right? The ordering. So, but Pearson partial correlation will give you this. It will put this thing over there, like there is really you don't know where this mass is located. This order is arbitrary, but it will, and then you will say, well, but physically, Euclidean distance it's far away, etc., etc. So I think something like that may be happening. But basically, you need
I
to.
think it makes sense.
Yeah. You just need to know
The,
what each thing is measuring. Or what, like,
yeah. I guess they just wanted to see if all those methods are either correlated or correlated with the distance. They should be unrelated on this.
yeah, so they're saying, well, 0.3 is kind of high and kind of low as well, but they're saying the further away precision would be more likely to be correlated with the distance, and correlation would be less likely to be correlated with the distance.
But all of those methods shouldn't be, they want those methods to be as correlated or as anti-correlated as they can. It's like a measure of their willingness for this criteria.
I don't understand what you said, sorry. What do you mean as anti-correlated or as correlated? Why would you want that?
It's something they expect from the brain. And that idea that distant regions are less connected than close regions.
No, I don't buy that. I mean, this is not true. Brain is connected in multiple ways. Cortex is connected by dendrites across each other. So, like, if this is our brain simplified, this is our cortex. Yes, those are connections, but there are cross connections, tons of them as well. And then, like here and here, you appear because it's a teleport. It's a fiber. There's nothing happening in between. It takes signal from here directly to here. It's not, and yes, you are connected sideways, but you also can. So the brain is not like, planet Earth. You have to travel geodesically.
I guess the idea is that those closer regions connected, and they are also stronger connected than distant regions. So on average, you will see that this intercorrelation of the strength of connection and the distance between
Correlation, but correlation that is just correlation, has no meaning.
Yeah, but it's a value they can compare.
Yeah.
It's,
But that doesn't help me to know how the brain works.
well, yeah, that's kind of the problem.
I feel like maybe the purpose of this figure is like showing how the different measures like capture information flow differently between the brain regions.
and that,
Maybe I'm a little confused about the takeaway from this.
Yeah, like we need to understand what correlation means, how it is not related to any causal interpretation. Like it is not.
Mm.
And I mean, this is not a magic, no, it's just a measure. Yeah, things act together, but it doesn't mean they influence or anything. So partial correlation, a little bit closer to the influence, but it's also just second order, etc., etc. And as long as we understand what these measures are doing, and that's kind of going into signal processing, electrical engineering, we'll be fine. Like I don't agree with the statement the brain should work like that. No, it shouldn't. It's like the data-driven part is the data will tell me how the brain works, but because there are like those connections are closed there, but maybe they play no role. The messenger comes in, tells me what to do, and everyone starts doing it. Yeah, the nearby things will be doing things. It doesn't tell me about how the brain works. It's just the messenger is the algorithm. It's like even though it is sparse and comes rarely, gives the order, and the brain, the neighboring things do the stuff. So that like the fact that the neighboring things are active doesn't mean like they're connected in any ways, because they also can be active, as we know from ICA, in statistically independently. They can be close by, but doing completely different things. They're both active, but and even correlated, but independently.
do you think it's not a good metric at all, or it can?
Depends on the questions you're asking.
It's just, I guess, there isn't many metrics that can tell us something meaningful and can be comparable between different methods.
No, look, as long as we understand those are just numbers, just measures of something, but not measures of everything. So here's the thing that it measures. So that when this goes up, this goes up. That's it. Like that's what it measures. When this goes down, this goes up, or if it's negative, they tend to go in the opposite direction. Fine, that's correlation. It's a good feature for prediction. Okay, good. But what if your question is different? It's like the science part is you have to be driven by, and we are by what is your question?
Well, question, I guess.
No, I'm not asking you. I'm just saying.
What is the paper's question?
Benchmarking, comparison of different methods.
So they are taking a similarity measure between these statistics coming from the methods, and then
they compare them in different ways. The similarity was one of them. Yeah, it's based on Spearman and Rowe. Basically, every figure has some method behind it.
Okay.
But yeah, it's just a set of benchmarks. They try to compare different methods.
Yeah, and I'm not critiquing the paper. I'm just trying to kind of widen the context.
Another method they came up with is the comparison of FLC with structural connectivity, which is derived from diffusion MRI. So it is.
Oh yeah. They're supporting this.
They expect that they should be somewhat similar, and they see that there are methods that are more similar, there are methods that are less. Precision again, I don't know why. Anyway, then they take a step.
It's a beautiful picture. I don't know what it means.
Yeah, they basically introduce another framework for time series analysis. And this first row is a method. It basically describes how it works. So assume you have two time series and you want to find out what kind of information is shared between them, what is redundant, and what you can get from when you have them together, what is the synergy. So it basically tries to define this framework for analysis of this data, and they apply it to the fMRI data and derive these FMCs, kind of FMCs, and then they compare the methods with these matrices. So far, but it's like one of the last thoughts. So this framework, as I understand, it allows you to categorize information you have in different sets of data. What kind of information is shared between them and what it looks like, what is the unique information to one data or region, what is it to another, what you can tell when you connect them together, what is the synergy information. It's like when you see letter T and letter H together, when you see them together, you can expect that the next is E. That's like a synergy information.
It looks like Christian could have come up with something like this.
Yeah, it's very like Christian. But anyway, they apply this method and then they again compare all of the statistical tests and FNCs to these results. And they show that I guess most of the methods are picking up the information which is shared between the channels with redundant information. But I guess the significance of this result is correlated with how much trust you have to this method. And I don't know, I get information. It's an interesting, I'm not sure. Maybe we could try it sometime without it. Without methods.
Yeah, they have the code available.
So yeah, to sum up, they compared the different methods for FNC derivation. They found that FNCs can look very different when derived with different methods. They kind of behave in the expected way on the benchmarks they find, but those benchmarks don't tell us really much on how useful they are for the understanding of the brain. They kind of give you a proxy, have an understanding of what those methods can derive, but not much else. ChatGPT for all the pictures.
It will appreciate you when the overlords take over. Yeah, thanks everyone for listening.